For the related rates problems, I'm going to cover the highlighted numbers 16, 18, and 19, but I'm also going to help you get started on the other ones 15, 17, and 20. Water slowly evaporates from a circular shaped puddle. The area of the puddle decreases at a rate of 49 pi inches squared per hour. Assuming the puddle retains a circular shape, at what rate is the radius of the puddle changing when the radius is 5 inches? Okay, I'm going to highlight important things. Circular shaped puddle, it retains its circular shape, so we're dealing with a circle. And what part of a circle? Oh, we're dealing with the area of the circle. The equation for that is A equals pi r squared. Then they said the area of the puddle decreases. So the area is what they've given us. The rate that the area decreases is 49 pi inches squared per hour. But this is decreasing because the water is evaporating, leaving the puddle. So this should be a negative rate. And then it said, what rate is the radius changing when the radius is 5 inches? So they want to know dr dt when r is 5. A conical paper cup is 20 centimeters tall with a radius of 10 centimeters. The cup is being filled with water, so the water level height rises at a rate of 2 over h centimeters per second. At what rate is water being poured into the cup when the water level is 5 centimeters? Okay, we're dealing with water being filled into a cone. That's volume of a cone. And the equation for volume of a cone is pi thirds r squared h. The water level, or h, rises. At what rate is water being poured into the cup? So volume, how is the volume changing when the height, the water level, so h, when h is 5 centimeters. The problem here is that when I derive this equation, I'm going to end up with a dVdt term, a drdt term, and a dHdt term. That's just the way it goes. But the only information that I got here, or it appears that I got, was dHdt and dVdt. I don't have drdt. So what I want to do is I want to write this entire equation with only the variables v and h. I do not want r, so I want to write r in terms of h. I'm going to show you how to do that after we finish these. A spherical snowball melts at a rate of 256 pi over 3 inches cubed per second. At what rate is the radius of the snowball changing when the radius is 7? So, sphere, and it's the volume of the sphere, because the snowball is made completely of snow. So we're taking volume of a sphere is 4 thirds pi r cubed. See, this one only has an r and a v already, so that's nice. So the entire snowball is melting at this rate. That's the change in the volume of the snowball, dv dt. And since it's melting, this is going to be a negative rate, kind of like the water evaporating, 256 pi over 3 inches cubed per second. And he said at what rate is the radius changing? So find dr dt when the radius in this case is. An observer stands 700 feet away from a launch pad to observe a rocket launch. The rocket blasts off and maintains a velocity of this, where a is the altitude of the rocket. Assume the scenario can be modeled as a right triangle. How fast is the observer to rocket distance changing when the rocket is 2,400 feet from the ground? So I actually drew a sketch. The person, here's the person, and here's the rocket. The person is standing 700 feet away, and the altitude of the rocket here is A, and we'll call the distance from observer to rocket Z. And so we have a right triangle, we can use the Pythagorean theorem as our equation for this one. And in this case, it would be a squared plus 700 squared equals z squared. Then they gave us the velocity, so how quickly the altitude is changing. So dA dt is 2,000 over a feet per second, and they want you to find the rate of change of z, dz dt, when the rocket's 2,400 feet from the ground, so when the altitude of the rocket is 2,400 feet. A 13-foot ladder is leaning against a wall and sliding towards the floor. The foot of the ladder is sliding away from the base of the wall at a rate of 5 over x feet per second. This can be also modeled by a right triangle, and we'll call the base x and the height y, and of course this is your ladder. Again, we'll use Pythagorean theorem. This was a 13-foot ladder, so x squared plus y squared equals 13 squared. The foot of the ladder is sliding away from the base of the wall, so that would be the x distance is changing, dx dt, at 5 over x feet per second. How fast is the top of the ladder sliding down the wall? So they want us to find dy dt when the top of the ladder, so when y is 5 feet from the ground. Number 20, a perfect cube-shaped ice cube melts at a rate of 64 over v millimeters cubed per second, where v is the volume of the ice cube. Assume that the block retains its cube shape as it melts. At what rate are the sides of the ice cube changing when the sides are 2 millimeters each? So the volume of a cube is taking the side length and cubing it. Right? It's a perfect cube, not a prism. So this one only has two variables, nice and easy. They gave us the rate of change of the entire volume of the cube. So dv dt is 64 over v millimeters cubed per second. That's a nice m, where v is the volume. At what rate are the sides changing? So they want us to find ds dt when the sides, so when s equals 2 millimeters. Now, in number 20, you're going to have to give them the volume when s is 2 millimeters. What is the volume? Okay, volume when s is 2 millimeters. Oh, that would be 8 millimeters cubed. Okay, so some information you have to kind of find out of what they've given you. Let's do the highlighted ones, starting with number 16. Like I said before, we're going to have to rewrite this equation before deriving it, all in terms of h. And we can do that because they gave us some measurements of the cone. It's 20 centimeters tall, so the height of the cone is 20 centimeters, and the radius of the cone is 10 centimeters. I'm going to write a proportion. The radius over the height is equal to 10 over 20. So now, can you write r in terms of h? Yes, you can. We're going to solve for r. So multiply both sides by h. r equals 1/2 h, or h over 2. So this is what we will replace r with in our equation. V equals pi thirds times 1/2 h product squared times h. And I will simplify this to be pi thirds over, this is like h over 2, so h squared over 4 times h. So the equation is actually pi over 12 h cubed. And now we have the volume of this cone written all in terms of h. Derive with respect to t. This is dv dt is equal to, I'm going to take pi 12ths out of the derivative of h cubed. The derivative of h cubed is 3h squared, and then the derivative of the inside, so times dh dt. 3 over 12 is 1/4, so pi fourths h squared dh dt. Pi fourths times h squared, h is 5 times dh dt, which is 2 over h, 2 over h. Oh, but in this case, they want to know when h is 5, so we're going to plug in 5 for h. This does reduce. 5 squared over 5 to the 1 is just 5 to the 1, so you'll have 5 in the numerator. 2 over 4 is 1/2, so you'll have 2 in the denominator. And with pi in the numerator as well, 5 pi halves centimeters cubed per second. Our equation only has 2 variables, so that's okay. We're going to derive it now with respect to t. The derivative of a squared with respect to t is 2a times the derivative of the inside dA dt, plus the derivative of a constant. 700 squared is just a constant, so that's 0, equals the derivative of z squared is 2z dz dt. And what they want us to find is the dz dt, so I'm going to get dz dt by itself by dividing both sides by 2z. dz dt is a over z, because the 2's reduce, times dA dt. Okay, so we've derived it, and then they want us to find dz dt when a is 2400. So we just need to plug in our a, our z, and our dA dt. We have the dA dt, we have the a, but we don't have z. So we need to know, what is z in this moment of time? Well, in this moment of time, they've said when the altitude is 2400. So what is z when the altitude is 2400? Okay, let's plug it in to this equation. 2400 squared plus 700 squared equals z squared. This is a Pythagorean triple, and z is 2500. So when a is 2400, z is 2500, and that's essential to solving the rate. Okay, so now we'll plug it in. dz dt when a equals 2400 is 2400 over 2500 times 20,000 over a. They said when a is 2400, so plug that in. 2400 over 2400 is 1. dz dt ends up being 20,000 divided by 2500, and that is 8 feet per second. That's the rate that the distance from the observer to the rocket is changing. And our last one, let's derive both sides of our equation with respect to time. The derivative of x squared with respect to t is 2x, the derivative of the inside dx dt, plus 2y dy dt, equals 0, the derivative of a constant. We are going to be trying to find dy dt, so let's get that by itself. Subtract 2x dx dt on both sides of your equation. 2y dy dt is equal to negative 2x dx dt. Okay, so what are they asking of us? They're asking us to find dy dt when dx dt is 5 over x and when y is 5. So we have a y value, and we have a dx dt value that has an x in it, and then we just have an x. And we don't have something to plug into that because we didn't find it. So we need to find that using the Pythagorean theorem, x squared plus y squared equals 13 squared. And they're saying when y is 5. So x squared plus 5 squared equals 13 squared. This is another Pythagorean triple. X is equal to 12. So when y is 5 feet, x is 12 feet. And that we now have a value for. We can plug in. dy dt is equal to negative 12 over 5 times 5 over x. What is x when y is 5? X is 12. Oh, that's just negative 1. Negative 1 feet per second is the rate of change of the ladder as it slides down the wall. So the rate of change of y.